An inventor is developing a paint stripping system that will compress air from atmospheric conditions, 1 bar and 22 degrees C, and supply it to a nozzle. At the nozzle exit, the air will return to atmospheric pressure. A 75 kilowatt motor is available to run the compressor. The objective is to produce a mass flow rate of 0.5 kilograms per second. The compressor and nozzle processes are both polytropic, with indices of 1.4 and 1.3 respectively. What air velocity will this system achieve at the nozzle exit? And the universal gas constant is given here as well if we need it. So this is an open system analysis. There's two components in here, a compressor and a nozzle. So let's start our given information with a little sketch of this system. So we've got a compressor. The symbol we normally use for a compressor is this. And of course it has a shaft supplying it with work. Air is coming in, air is leaving, and in this case it's entering a nozzle. So put the flow direction on here and number these state points 1, 2, and 3. Now let's get the other information that we know on here. Inlet conditions to the compressor, 1 bar, 22 degrees C. So P1 is 1 bar, T1, 22 degrees C. At the nozzle exit, the air returns to atmospheric pressure. So we know P3 is also 1 bar. 75 kilowatt motor is available to run the compressor. So the work input here in the compressor, the rate of work input, is equal to minus 75 kilowatts because it's a work going into the system, so it's negative. We're hoping to achieve a mass flow rate of 0.5 kilograms per second, so the mass flow rate through this is 0.5 kilograms per second. And notice each of these components just has a single inlet and a single exit. So it'll be 0.5 kilograms per second throughout. Now, also we're told a little bit about the processes from 1 to 2. So 1 to 2 is polytropic with an index of 1.4. And 2 to 3 is also polytropic, but with a little bit lower index. So the processes through here are not the same, but they're both polytropic, just a different index. And the final thing of interest in the problem statement is the fact we're asked to find V3. And notice now, because we've numbered our state points, we can state the information we're asked to find symbolically, V3. So that's what we're after. Next step is always an assumption list. Now in this case, we're going to build that assumption list as we go along. So we'll be coming back here periodically and adding assumptions to it. So I'm just going to leave some room. And we're going to start this analysis. Now it's an open system analysis because it doesn't matter which one of these components we decide to look at, or if we decide to look at the entire system as a control volume, we're going to have an open system. So let's start our analysis by looking at the open system energy equation. So this is conservation of energy for an open system, and it is essentially the starting point for every one of these problems. So rate of change of energy in the control volume with respect to time, heat transfer rate, work transfer rate, and then finally we need to recognize that there are inlets. So we have mass flow rate inlet, H inlet, kinetic energy term, and potential energy term. And the same thing happening at exits. But of course the sign for all these is negative. So H exit, enthalpy, kinetic energy at the exit, potential energy at the exit. So that's our starting point. Now what we're going to do now is think about the assumptions we can make to this equation that are valid regardless of what component we choose to look at. And the first of those that we'll do is steady flow. So steady flow, so that is going to be gone. I'm going to go back and add these to the assumptions. Oh, there, I can fit it all on. So let's go back here and say steady. That's all we need to say. Steady state, if you wish to be a little more specific, that's fine. Heat transfer is next. Well, neither of these components has substantial heat transfer with the surroundings. We're talking about a turbine and a nozzle. There are no heat exchangers in here, so we're going to put up here that the entire system is adiabatic. So we'll just say adiabatic. Compressor and nozzle. In other words, everything. Work transfer we certainly need to keep because of the compressor. Inlets, well, all of these components have just a single inlet and single outlet, so we'll see these summation signs disappear. The potential energy is 0 everywhere. Okay, so we're ignoring potential energy. So neglect potential energy. And also, the kinetic energy is going to be 0 everywhere except the exit of the nozzle. So inlet kinetic energies we can get rid of here. So kinetic energy negligible except at 3. So everywhere except the exit we can neglect kinetic energy, and that's typical assumptions for these components. So now we need to look at specific components. And what I'd suggest we do is, because we were asked to find the nozzle exit velocity, let's look at a control volume around the nozzle. So we state here, and we'll go to the getting the next page here to do this. That we're looking at the nozzle. Okay. Well, in addition to the assumptions we've already made, the work is 0 in the nozzle. So let's go back up to our assumption list and say work equals 0 for nozzle. And that's certainly true because there simply is no shaft sticking out of the nozzle. So what we have left is mass flow rate at 2 times the enthalpy at 2 must equal the mass flow rate at 3 times the enthalpy at 3 plus V3 squared over 2. And of course these mass flow rates are the same, so they can cancel. Now the problem that we have, we're looking for this V3, so that's fine. But we don't know H2 or H3. Remember, the substance here is air, so in order to determine the value of the enthalpy, we need to know the temperature. And if we go back to our given information here, we don't know the temperature at 2 or the temperature at 3. The only place we know the temperature is this inlet. So this is a real dead end temporarily. There's two things, in fact there's three things in that equation we don't know. The velocity, which we're after, so that's fine, but we don't know either of the temperatures on either side of this component. So we're going to have to temporarily set that equation aside. Now remember I said that in order to calculate those enthalpies, we need to know temperatures. That's because this is an ideal gas. So we should add that to our assumption list, that we're going to assume this is an ideal gas. Now I've run out of room here a little bit, but I'm going to put it up here. So we're dealing with an ideal gas. Okay, well, setting the nozzle aside for a moment, we'll go to the compressor and see what it tells us. So again, first law for the compressor side of things, and of course kinetic energy is 0 on both sides, so the work rate of the compressor is going to be the mass flow rate through it, and I don't put a subscript on this mass flow rate because by now we've recognized that it's the same everywhere. But that'll be H1 minus H2. Well, T1 is equal to 22 degrees C, which is equal to 293 Kelvin. So because we know the temperature at the inlet, we can go and get this enthalpy value directly out of table A22. So if we go to table A22 at 293, we find the enthalpy is 295.17 kilojoules per kilogram. So that's coming from table A22, the ideal gas table for air. So we know the work, know the mass flow rate, we now know H1, we can calculate H2. So putting numbers into this, critical to remember that the work is negative because it's work done on the system. 0.5 kilograms per second is the mass flow rate. H1, 295.17. H2 is the unknown, and the units on both those H's, kilojoules per kilogram. And so that H2 works out to 445.17 kilojoules per kilogram. And we can go into table A22 and figure out what the temperature is, just interpolating backwards. So that works out to 443.5 degrees Kelvin. Again, that's from table A22. So if you think about the problem we had with the nozzle, we've fixed half of that problem because we now know the enthalpy at the inlet to the nozzle. But we still don't know the enthalpy at the exit of the nozzle. Now we know something else about the nozzle process. We know it's a polytropic process. However, we don't know the pressure at the inlet to the nozzle. So the first thing we're going to have to do is look at the process through the compressor to get the pressure in the nozzle, or at least at the inlet to the nozzle. So what do we know about the compressor? Well, we know P1 V1 to the 1.4 equals P2 V2 to the 1.4. And this is a polytropic process course which we were given. Now, specific volumes are kind of inconvenient to work in, so we're going to do the same thing to this as we've done many times. We're going to use the ideal gas law to eliminate these volumes. So first of all, put this in terms of ratios. So P1 over P2 is V2 over V1 to the 1.4. And this volume ratio I can rewrite using the ideal gas law. So V2 is equal to RT2 over P2, and V1 is equal to RT1 over P1. These R's cancel, and we get T2 over T1 times P1 over P2. So the specific volume ratio has been written in terms of temperatures and pressures. Now we can bring this back into there, and we get P1 over P2 equals T2 over T1 times P1 over P2 to the 1.4. Only problem with this, we've got pressures here and here, so we'd like to bring those all together. So P1 over P2 to the 1 minus 1.4 will equal T2 over T1 to the 1.4. And then finally, take all these exponents to one side. So 1.4 divided by 1 minus 1.4. So we've done that lots of times, but it relates the pressure ratio across this component to the temperature ratio. Now if we think about what we know in this problem, we know both of these temperatures, and we know this inlet pressure. So we can solve this equation for P2. And that's critical information here because it allows us to go to the nozzle here in a moment and figure out the temperature at its exit. So P2 will be equal to P1 times T1 over T2 times 1.4 over 1 minus 1.4. And finally, this is ready for numbers. P1 is 1 bar. And the temperature ratio, 295 over 443.5. Remember, those have to be in Kelvin. 1.4 divided by 1 minus 1.4. This works out to 4.166 bar. So that's the pressure, the exit of the compressor, or the inlet of the nozzle. Now, the polytropic process across the nozzle is the same as across the compressor, only it has a different index. So all that work we just did, we can use. So similarly for the nozzle, we can say, and just going back partway through that development and writing it in terms of state point 2 and 3 instead of 1 and 2, we can start here. And I'm going back to this stage because in this case we want to solve for temperature from known pressures. So from this we can say that T3, so just solving this for T3, is T2, P2 over P3, 1 minus 1.3 over 1.3. And again, we know all these numbers, so we can put them in and solve for T3. So our T3 is 443.5 degrees Kelvin, that's T2. Ratio of pressures is 4.166 divided by 1. Remember, the exit pressure is 1 bar, and our exponent 1 minus 1.3 over 1.3. So T3, 319.07 Kelvin. So notice the air cools down as it goes through the nozzle because it's accelerating. Kinetic energy goes up, enthalpy goes down. So we now have T3, so we can look up H3, and that's from table A22. So that becomes 319.35 kilojoules per kilogram, and that's table A22. So finally, we've got the enthalpy on both sides of this thing. So we go back to the first law for the nozzle, which we already worked with, and we already simplified it down. So we just restate that here. H2 is H3 plus V3 squared over 2. V3 is what we're looking for, and we know everything else. So solve for V3 is going to be equal to 2 H2 minus H3, and we'll be taking the square root of that whole thing. So last thing to do here is put numbers into this, and H2 is 445,170, and H3 is 319,350. And notice the units on both of those I'm putting in as joules per kilogram, not kilojoules per kilogram. So that's why these numbers are so big. I've multiplied them each by 1,000 to get joules per kilogram. And that's because if we want the units on this velocity to work out to meters per second, which we do, these energies have to be in joules per kilogram, not kilojoules per kilogram. So V3 works out to 502 meters per second. So this paint stripper that the person has invented is going to produce a stream of air, half a kilogram per second, moving at 502 meters per second. So that's a fairly substantial velocity when we think about it. So that may indeed be capable of stripping paint. But if you take a look at the power input to this compressor, remember up top here, they're using a 75 kilowatt motor to do this. That's 100 horsepower. So this is a fairly substantial motor that he's got running this thing. So he may have a paint stripper, but it's a fairly powerful beast, and he's going to have to hang on pretty tight, I think.